Good day, everyone. This is Shahram, and this is the second lecture on Physical Science Survey course, PSCI 10 at West Valley College. So today we are going to talk about motion, but before we do that, let me just recall what we talked about last time. So we are going to cover the physical science disciplines that covers physics, chemistry, astronomy, and geology. So in each one of these fields, we're going to touch upon some of the fundamentals. In physics, we're going to talk about classical mechanics and Newton's law. We then talk about concepts of energy, heat and temperature, wave, electromagnetism, optics, and atom and nucleus. In chemistry, we talk about elements and periodic table, chemical bonds and chemical reactions, and a little bit about water and solutions. And time permitting, we'll talk about organic compounds and some nuclear reactions. In astronomy, we're going to talk about the universe in general, the formation of galaxies and concept of dark energy, dark matter, and a little bit about our solar system. And in geology, we are going to discuss the Earth composition, the inner part of the Earth, plate tectonics, how they move, seismic activity, earthquake, and time permitting, we talk about a little bit about the weather system. We will explore applications and phenomena that overlaps between any one of these disciplines and try to bring in everyday life application on phenomena that we can explain based on these concepts. So now let's start chapter 2, which is about motion. So we are going to look at motion and define speed and velocity and acceleration, and talk about force and Newton's law, concept of inertia, introduce concept of free fall and non-free fall. And then we will talk about momentum and impulse and their relationship between momentum and impulse. Then we will talk about the combined motion of linear motion as well as the accelerated motion, which can produce a projectile motion. And then we conclude with Newton's universal gravitational law and some applications. So if you look at the landscape of physics, covers 4 areas. One is classical mechanics, which deals with the large size objects, astronomical object, all the way down to objects of ordinary sizes that we are familiar with. And the speed of smaller speeds, all the way to measurements with our instruments, be able to analyze and applications in that domain. Then we move down to smaller and smaller sizes in atomic size, then the laws that govern by quantum mechanics. As you increase the speed for the large and ordinary size objects, then we talk about relativistic mechanics, special relativity. And what happens if things start moving at very close to speed of light. On small size and very high fast speed, which the field of quantum field theory, which we don't really cover that in this course, but all of these areas also covers electricity and magnetism, applies to many, many phenomena in physics. Trying to understand the motion and how motion is relative. When we just sit on our chair, are we still, are we moving? Well, we think that we are stationary, comfortable sitting on our chair or couch, and nothing is moving. Well, that's from the perspective of the world that's surrounding us. When we move with respect to some stationary reference. But what if that reference is moving too? So if you're running with respect to, say, a bus that is a stop, you're going at certain speed, but once you're moving and the bus is moving, then your speed relative to that would change. Basically, every motion is relative, and that's the underlying concept here. And in order to understand the motion, we have to always consider motion with respect to some reference. If you really look at it realistically, everything in the universe is moving. Nothing is motionless. And that motion is very fast with respect to what we are familiar with and very complex. Let's take a look. While we are sitting and watching this lecture here, the Earth is actually rotating around itself at 40,000 kilometers in 24 hours. So that's roughly 1,666 kilometers per hour or 1,000 miles per hour. Earth is also orbiting around the sun every year. And that's roughly 66,000 miles per hour. And then when we look at the solar system, which we are part of it, is spinning around the center of Milky Way at 420,000 miles per hour. All of these are approximate. And then Milky Way itself is moving in space approximately at 2.2 million miles per hour. So look at all these speeds here. If you add these all up, you come out with a number as 2.7 million miles per hour or 4.4 million kilometers per hour. Now, this is not just a straight line movement. This is a very complex motion. And if you compare that to, say, speed of light, which is 670 million miles per hour, approximately 1 billion kilometers per hour. So we are still moving much, much slower than the speed of light. But the interesting part is that we are moving at very complex motion. So let's watch this video. So you can see that the sun is moving and all the planets around it is following it. And the motion is a very complex motion called vortex. And the sun is really not moving straight because it is part of the rotation, the Milky Way. So add on top of that rotational motion. And then the Milky Way galaxy also is moving in some complex motion with respect to the next galaxy, Andromeda. So they're kind of rotating around each other, around their center of gravity. So all these motions can affect indirectly So look at the shape of some of the things that we're familiar with in our everyday life. Why is it the shape are like this? So as you can see, we are moving and we are moving in a very complex way in space. And that motion does affect things around us. And for example, look at some of the phenomena that we experience. And these are some examples that because of our motion, perhaps all of these shapes are influenced by this accelerating motion that is there constantly, but we are not feeling it, or at least we are not aware consciously. So now let's talk about some of the fundamental quantities can describe the motion. Those quantities are position, displacement or distance, speed or velocity, acceleration, and time. So we're going to talk about these in more details. And one thing we need to distinguish between some of these quantities, that some of them are just the pure scalar quantity and some of them are vector quantity. Now, what do we mean by that? Well, vector quantities is a quantity that has both magnitude and direction and is represented by arrow. The length of this represents the value of that velocity, let's say 5 meters per second, and the direction, let's say at 30-degree up, x and y coordinate. Whereas the scalar quantity is number, which represents, so mass is a scalar quantity, volume is scalar quantity, speed is scalar quantity, but velocity is a vector quantity. Now, when we talk about the motion, we are going to try to separate the motion in two categories. One is a straight line. So a straight line motion is basically a motion that doesn't change its direction. It just goes in a certain direction. And then non-straight line motion can be a circular motion. It could be elliptical or spiral or vertex, as you just saw. So let's start with a simple case, a straight line motion, and then we move on to more complex motion. First thing, we need to define some of these quantities. When we talk about position, we say an object has a position with respect to a coordinate. Usually we show that some sort of a coordinate system. If it is one-dimensional, you just have to show it with one arrow direction. If it is two-dimensional, you show it with x and y axis. And if it is three-dimensional motion, you need to show with x and y and z axis. Of course, there are other coordinates like polar coordinates and so on, which we don't discuss that in this course. When there is a motion, it means that the position of an object is changing in time. So when we are looking at concept of a distance is the path that you travel from a point A to B. So for example, you're going from the bus stop to your class. So you have to navigate through the buildings, sidewalks, and so on. So that's your path. That's your distance you cover. However, if you had a kind of a little helicopter, you would just go up, straight go from A to B. And that would be your displacement. So the difference between the distance and displacement is a straight vector from point A to point B, whereas distance is a path that you basically go to get from A to B. And of course, displacement is a vector quantity, distance is a scalar quantity. Now we can ask the question whether speed and velocity are the same thing. Common sense says, well, they're probably the same thing, but they're not. When you're considering the motion in physics, you need to distinguish between the two. Speed and velocity are not the same. Speed is a scalar quantity. It just tells you how fast something is moving. Whereas velocity, it tells you not only how fast something is moving, but in what direction. So we need to consider them separately. So these are some examples here. We walk 4 miles per hour, what we don't tell you which direction. So that's our speed. But if you say I walk 4 miles an hour towards a bus stop or towards the shopping center, that is velocity, because now you're specifying a direction. Okay, usually we specify the direction by an angle, because once we have a coordinate system of x and y, and say we want to go from point A, we just start at origin A to point B, we have the vector from A to B, and the angle here, theta, defines the direction. You can define a direction different ways too. You can say northwest or east, south, or whatever. Let's talk a little bit about vectors. For some of you may not be familiar with vector quantity. Vectors are a simple way to represent quantities that have both magnitude and direction. For example, the length of the vector represents the magnitude. So if I look at these 1, 2, 3, 4, 5, 6 units here, that would be 6 magnitude. So here we have the vector 3 unit plus a 7 unit, it gives you a 10 unit vector in same direction. Now, if you have a 10 unit vector, but you have a vector that is opposite direction, let's say 3 direction, then you have to subtract that. So here on top, you add them. Here you subtract them. So you have 7. And here you have 2 vectors that are same direction, but they're not aligned in one line, but still you can add them because they both are in same direction. So you have a vector of 8. Now, they may not be parallel, they may not be aligned in same line. So what do? Well, you use a little bit of a geometry. So if you have a vector that is going up and a vector that's going to the right, you form a triangle. So let's say you start with the A. So you have A going up. And let's say my actor B is somewhere here. I just take the tail, put it on the tip of the A. Okay, so that's A, this is B. And then parallel to that, I put this. And then the vector here would be the addition of A plus B. And then you use a little bit of an arrow on top of these to basically denote that these are vector quantities. All right, there are different ways of doing that. So alternatively, if I have A like that, and my B is still up there, so I can, rather than putting this on the tip of the A, I put this at the tail of it, and I just write this like that, B. And now I have to form a square here, and then this would be A plus B. These are basically just a review. Take a look at these examples here. And if you're not familiar with it, try to familiarize yourself. And then we use a lot of examples later on that you can actually get a hang of it as we go on. What about the direction? How do we assign a positive and negative direction? So if you look at the coordinate system, X and Y, anything that goes up and to the right, any vector that is up and to the right, you assign a positive sign to it. Anything that goes up and the left is negative, or going down and left is negative, or going down is negative, or going down and right is negative. So keep this chart handy. When we form our vectors, make sure you put the negative or positive sign next to it. Now, we talked about speed. Let's talk about instantaneous. Well, it means that at any instant of time, whatever that your speed is called instantaneous speed. And a good example on that is while you're driving your car, of course, you're watching the road and all that, all of a sudden you see a cop there. You look at your speed to see how fast you're going at that instant. That's your instantaneous speed. You can show the motion by a graph representation, because we know motion involves distance and time. If you have one axis of your graph as a distance that an object travels, and the other axis a time, then the graph that you see here represents how that object is moving. From here to there, if you look at this graph, so this is 10 second, 20, 30 second. This object is moving from 0 to 100 meter. It's actually moving at a constant speed up to 30 seconds. Then it's not moving for another 20 seconds. Nothing is moving right now because it's still sitting at 100. And then it's moving from 50 seconds to 70th second to 400 meters. So it's moving faster. The graph reveals information. The slope of this graph tells you what the speed is. Because look, slope is equal to change in y-axis over change in x-axis. Looking at this, my y-axis is distance. Okay, so it's actually change in, say, delta distance divided by delta. Delta means change of time. So change of t, time. And this is definition of speed. In this case, speed, because we're not talking about the direction. There's no direction indicated here. So that's how you define this. So here, it's 100 meter per 30 seconds. So you're moving at 3.3 meter per second. Here, you're not moving at all. Here, you're moving at 300 meter in 20 seconds. So you're moving at 15 meter per second. So you're moving much faster. So you see how to interpret. So if I give you a graph and ask you to interpret that graph, you should be able to do that just by taking the slope of these lines. We have a situation that you go from point A to point B, and it takes about, 70 seconds to get there. And you go slow here, you stop a little bit, and you go faster. So the question is, what is your average speed? Okay, well, you can do that. Average speed is basically the total distance you cover. What is the total distance you cover? You go from 0 to 400. That is the total distance. In total time, you go from 0 to 70. So 400 meters per second, that's 5.7 meters per second. So that would be your average. So that's a definition for average speed. So question for you. The average speed of driving 30 kilometers in 1 hour is the same as average speed of driving. Which one of these is correct? Now, by the way, a lot of these questions that I pose here in the lectures are similar to the question you will see in the quiz, homework, and tests. So make sure to review these all the time and get a good handle on it. 30 kilometers in 1 hour, it's 30 kilometers in 1 hour, okay? So that's equivalent to which one of these guys? So let's see, if I have 30 in 2 hours, that's not going to be the same number. If I have 30 in half an hour, that's not going to be the same number. 60 in half an hour, no. So what about 60 kilometers per 2 hour? Because I can simplify that. This 2 and this would be 30, and then it would be 1, and then that would be the same. When we talk about constant speed, we talk about the number, speed without the specifying direction. When we say car is moving 70 miles per hour, a straight highway, you're showing a direction there. Airplane cruising at 600 miles per hour in a straight line. Now, if the airplane is turning at 600 miles per hour at a constant speed, the speed is constant, but something else is changing. The direction is changing. So in this case, you have a velocity, because now when you're looking at 600 miles per hour straight, that's the speed. It goes straight in one direction. But when you say 600 miles per hour turning, That means it's going to do like that. Okay, so the direction is constantly changing. At any instant, the direction is changing. So that's its velocity. So that's called constant velocity. Okay, let's look at some graph. So let's look at this one. You have a distance and time, and you have a distance that is increasing in time. Yeah, if it tells you the direction, then it's going to be constant velocity. In this case, when it's not moving, the distance is not changing, you have zero velocity. In this case, you have a constant velocity, but in starting from origin. Here is you start from a distance to go to another distance. In this case, velocity is increasing in a nonlinear fashion. Now, the question for you is that suppose you have two airplanes just passing by each other, and they both have same speed, 300 kilometers per hour, but they're going in opposite direction. Question is, are their speed the same? Yes, speed is the same. What about their velocity? No, the velocity is not the same because they're in opposite direction. Speed is the same, but the velocity is not. So now let's talk about what happens when you are moving at a constant speed. When you're moving at constant speed, it is as if you sit in your living room. All the laws of physics applies. For example, if I toss a ball up and come back on my hand, I catch it, and all the laws of physics works just fine as long as you're moving in constant. In the airplane, when the airplane is cruising, you can walk around. If you toss a ball at somebody else, they can catch it, no problem. But what happens when the airplane is taking off? Can you do that? Or when it's landing? Or while you're in your car, you are actually getting off the exit. Then if you throw a ball, that's not going to go where you intended to go. That's where the acceleration concept comes to play. Whenever the velocity is changing in time, then you have to deal with acceleration. You have acceleration. Remember, position changing in time, you have velocity. Velocity changing in time, you have acceleration. We define acceleration as change in velocity in time. We show that with notation of A, and the change in velocity, we show that with delta V, and change in time, we show that with the notation of delta T. What does that mean? That means change in velocity is equal to final velocity minus initial velocity, and change in time is final time minus initial time. So if you have those numbers, you can find what acceleration is. Remember, velocity was delta x, showing the distance, delta t. The unit for velocity was what? X was position, right? So it was meter per second. Okay, so that's the unit for velocity. Acceleration is delta v, delta t. So now you have the unit for this is meter per second per second. So that means is meter per second squared. But there are things that acceleration changes also. We'll see some examples, simple examples of that too. A car is accelerating when it is, which one of these? Well, turning in a curve at a constant speed. We said because it's changing its direction, therefore its velocity is changing. When the velocity is changing, therefore it's accelerating. So A is true. Slowing down to stop. Well, when something is slowing down, its velocity is changing. So it's kind of decelerating. Deceleration is negative acceleration. It is accelerating. So B is true too. Stepping on a gas pedal to pass another car. Yes, you're going faster and faster. Therefore, you're accelerating. So all of these would apply. So velocity and acceleration are actually, well, let's see which one of these is correct. The same when direction is not factor. The same? No, they're not the same. Rate of change of different quantities. The same when object is no. Basically, it's a rate because we're saying change of position with respect to time, change of velocity with respect to time. That's the right answer. So when we write the acceleration like delta V over delta T or like this, we can actually rewrite this differently. So we can bring the T multiplied by that, and then you get this. So you get a different equation. I mean, they're all saying the same thing. It's just if you want to find the final velocity of something that is accelerating, you can rewrite this in this form. So this is the same equation as the acceleration equation. It's just written in different way. The car is starting from rest, accelerating uniformly in a straight road. It reaches the speed of 90 kilometers per hour in 7 seconds. What is that? It reaches the speed 90. So that's V final. So final velocity is that, but it starts at rest. So initial velocity is 0. So how long does it take? 7 seconds. So delta T is 7 seconds. We want to find out what is acceleration. So we use the definition for the acceleration. Acceleration is V final minus V initial divided by delta T. We are given 90 kilometers per hour, but is asking what is the acceleration in SI units. So we want to have to convert it to meter per second square. So we have to convert the velocity to meter per second. So first we do that. 90 kilometers per hour is equal to 0.278 meter per second per kilometer per hour. So you look this up or use your conversion app, and that gives you 25 meter per second. V final is 25 meter per second, V initial is 0, so, and then delta T is 7, and then you get 3.57 meter per second squared. So acceleration now is a vector quantity, okay? Now let's look at these cases here. This car is moving to the right. Remember, we said to the right, positive. Kind of accelerating. Velocity is increasing to the right. Okay, so acceleration is positive, velocity is positive. This car is moving to the right, but stopping. It's kind of slowing down. That means the acceleration is to the left. Now, this car is moving to the left. Now, the velocity is negative. Now, in this case, case B, acceleration is negative. In case C, velocity is negative. All right? But it's slowing down to the left. So acceleration is opposite of that. This car, acceleration is same direction as the velocity. So that means it's speeding up to the left. Now let's get back to what Galileo actually discovered. Remember, we talked about Galileo. He did a lot of contribution. He actually conducted an experiment. The experiment was that first he rolled a ball on an inclined surface and watch it. The ball is picking up speed and covering more distance as it goes down, assuming that there's no friction here. And then he tried to roll up the ball, and he noticed that the ball actually is slowing down and it stops at one point. And then he used the flat surface and he rolled the ball and watch it just continue moving at the same speed. He basically said that here the ball is accelerating, here is decelerating or is a negative acceleration, and here is not accelerating at all. It's just moving with a constant speed on a flat surface, assuming there's no friction. Because if there's a friction, the force of friction, as we'll see soon, stop the ball. What was his conclusion? Well, he said that when the ball is speeding down, accelerating, something is pulling it down. What is that? That's force of gravity. It's pulling it down. and then roll it upward, it's decelerating. The force of gravity still wants to pull it back down. So it makes it to go slower and slower and stop at one point. And then when you roll it on a flat surface, it just keeps going. As long as there's no friction, it can go forever. Of course, there's always friction. But if there was no friction, it would go forever. So there's no force acting. The force of gravity is not doing anything at that point. You may say, hey, it has something is pulling it down on the surface. We'll talk about that in a minute. The ball is on the surface. Of course, the force of gravity is pulling it down, called Fg. But there's another force that countering that, which call it normal force. So these two forces cancel each other. When we look at these two cases, that the ball is slowing down or speeding up, that's fine. But the third case, a little bit ambiguous. Now, Galileo came out with this idea that if the ball is moving, you set it to motion and let it go, something causing that thing to move constantly. And that was the concept of inertia. He introduced the concept of inertia, saying that the ball has inertia, and once it's set to move at a constant speed, because its inertia is causing it to continue moving. If you have a bigger ball, therefore you must have greater inertia. If you have a smaller mass, you must have a less of an inertia. Now, look at some examples that we encounter every day. You know why you have your seatbelt? Because of inertia. In the old days, when there was no seatbelt, when you get into accident, when you're going 70 miles an hour, all of a sudden, bang, you hit some car or some car hits you and car stops. Guess what? Your body still wants to move at 70 miles an hour. So what happens? You shoot off the glass. You know what happens then? You stop the car by applying the brake, but you had no way to stop. Your body is moving at 70 miles an hour. It has a lot of inertia. So that's why they put the seat belts. Your inertia wants to continue, move at the same constant speed as is. Or if it's stationary, it wants to stay. We are lazy. Bodies are lazy. Objects are lazy. If they're stationary, they want to stay stationary. If they're moving at a constant speed, they want to continue moving at constant. That's the concept of inertia. Another example, let's say you're riding a bus. You're holding on the handle there, and the bus is cruising at 30 miles an hour. And all of a sudden, he has to stop at the station. What happens to you? You're going to lean forward because your body still wants to go at 30 miles an hour. That's inertia. That's not a force. Now, the more massive, the more inertia. This big guy is harder to get him to swing. But that little girl, it's easier to push and get him to swing. Another things that you can try, people pull the tablecloth under the stuff on the table without disturbing them. If you move the tablecloth fast, the inertia of these objects, they want to stay where they are. They don't want to move. So they remain where they are. Try this. Put a whole bunch of quarter on the piece of paper on the table. First, move it slowly. You see that all the quarters comes along. But then rapidly move it. The quarters stay where they are. And the paper can be pulled out. So Galileo did another experiment, and that was to show that the gravity doesn't discriminate. What does that mean? He tried two different sizes of objects, say two round balls, one small and one more mass than the other one. He had an intuition that if you drop those at the same height, they're both going to hit the ground at the same time. And he demonstrated that. Of course, there's a little bit of an air resistance, but air resistance doesn't affect the shape of these objects as much. So they both felt at the same time on the ground. That was a counterintuitive, because people thought, hey, if you have a heavier object, it's going to hit the ground quicker than the lighter object. No, what you can do is you can use your textbook on one hand and the leaf of paper on another hand. Hold them at the same height. Okay, your textbook, heavy textbook and lighter piece of paper, drop them. You see which one hits the ground first. Obviously, the textbook is going to hit the ground first. Then go ahead and crumble the paper to a very small ball. The mass of this didn't change, right? So it still has the same mass. Now, drop them at the same height. You notice that they both follow the same. By crumbling that, you're kind of reducing the air resistance affecting it, and they both follow the same rate. Okay, so you can try that at home. So conclusion, Galileo basically said there's something is pulling these objects, and it doesn't discriminate. And it, regardless of their mass, it's going to affect every mass at the same rate. So they fall at the same rate. And then Newton took over, used that notion, and talk about the force of gravity causing an object to accelerate at the same rate. He introduced the concept of force. Force is a quantity that affects an object, either pushes or pull it, and it has a capability of changing the velocity of an object. He said that force and acceleration, therefore, must be related. So that's where Newton started putting things together. So first thing he said that if you apply a force to an object, that object is going to go faster and faster and faster. So he said it's proportional to acceleration. Now, if that object become heavier, or you have a heavier object, is not going to accelerate as much. So he said that acceleration is proportional to the inverse of the mass of the object. So the heavier the object, the less of an acceleration for a given force. And then he was able to put this together and say that acceleration is equal to force divided by mass. And that was Newton's second law. The first law is inertia. He was able to say that any object that is stationary is going to stay stationary, and any object that's moving at constant velocity is going to continue moving at constant velocity because of its inertia. And then the second law relates the acceleration to the force applied to an object and the mass of an object. So this relationship, you can write it like this, or you can write it like F is equal to ma, or you can write m is equal to F over a. So you can write it three ways. Now the question is, does force really cause something to accelerate? Well, we have to qualify that statement. It depends. If you have several forces involved, those forces, if they cancel each other, there will not be any acceleration, because the forces are vectors, so they can cancel each other. Look at these guys. These guys, girls are pulling to the right, and these guys are pulling to the left. But nobody's moving. They're putting a lot of forces there. They're really sweating, but nothing happening. They're both equal forces. So there is no balanced force, or there is no what we call it a net force. The force necessarily doesn't cause acceleration. It only causes acceleration when there is a net force. Now, net force is at the end of the day, add all the forces, subtract, depending on direction and all that, there still remains an unbalanced force that's called the net force. That net force is going to cause acceleration. So these guys are pulling harder, and this girl is going to be accelerated towards them because there's a net force. Distinguish between the force and net force. So let's look at some examples, simple ones. Here we have 500 Newton. Now, what do we call Newton? Well, let me just backtrack here. So let's look at the units. What is the unit of mass? Remember, look at the table I showed you before, kilogram. What is the unit of acceleration? We just discussed that. That was meter per second square. So kilogram meter per second square is the unit of force. In honor of Mr. Newton, we call that Newton. Okay? So whenever we talk about Newton, we mean kilogram meter per second square. 500 Newton to the left and 750 Newton to the right. So what do we have here? We have 250 Newton to the right. What about here? 400 to the right, 400 to the left, 0, no net force. So here we don't have net force. In this case, we don't have net force. In this case, we do have net force. It's 500 Newton minus 300, so it's 200 Newton to the left. Here we have net force to the right, 1000 minus 500, so 500 Newton to the right. Okay, so you get the idea, right? So net force is what you want to concentrate on. So go ahead and do this on your own and write down the direction and the net force for each case. So that's an exercise for you. So now we come back, take the Galileo's ideas, and Newton make that as his first law, called the first law as law of inertia. Objects will remain at rest or continue moving at uniform straight line unless there's a net force is acting, an external net force. The internal forces don't count. What do I mean by that? Internal force. Well, suppose you're sitting in a car. Your car is stalled. You need to push it to move it. Now you're sitting in the car and you're pushing a dashboard. You're pushing it very hard. Would the car move anywhere? No. You have to get out and push the car from outside. Pushing it in the dashboard inside the car, that's internal force, so that doesn't count. The force that you push from the back, that is a net force, and that caused the car to move. Now let's look at the example, analyze this. So we have a ball here that is actually the forces that are acting on it. Let's say the ball is moving on a flat surface, but there's air causes things to slow down, right? Air drag. We'll talk about air drag when we talk about non-free fall. Obviously, it's rolling on the floor, so floor has some friction. We'll talk about that later also. So that those two are against the actual motion of this. So the net force is the air drag plus the floor friction to the right. So there's a net force here causing this to stop. So there's a net force causing deceleration or negative acceleration. Now, in this case, if you push the car, apply a force that is equal and opposite direction to the net force, then you actually cause the ball to continue going at a constant velocity. And that means there's no net force. All right, some questions here. What happens when a net force acts on an object? Well, it produces an acceleration. We just talked about it. So net force causes something to accelerate. And then obviously the heavier the object is, the less of acceleration. So it's inverse proportionality. So putting all these together, Newton's second law, acceleration is equal to F net over m. Example. So here we have 5 Newton to the right, 3 Newton to the left, and the mass is 3. So what is the magnitude and direction of acceleration? So A is equal to force divided by the mass. So F net, I'm going to put F net here. Now we have 5 Newton to the right, which is positive, and 3 Newton to the left, which is negative, divided by 3 kilogram. So that is the case A. Case B, A is equal to plus 4 Newton to the right minus 3 Newton to the left divided by 1 kilogram. 2 Newton divided by 3 kilogram. And here you have what? 1 Newton divided by 1 kilogram. Let's look at this example. Now you have these two objects tied together with a rope. And this one is 1 kilogram and this one is 1 kilogram, both same mass. Side, the force is pulling it at 8 Newton, and this side is pulling at 5 Newton. Find the magnitude and direction of acceleration. So that's what we're looking for. Well, now we have a system. Okay, acceleration is equal to what? F net divided by the mass. Now, F net, it's 8 Newton minus 5 Newton. So it would be 8 Newton minus 5 Newton divided by. Now, mass is tied together, so we have to add them together. Okay, there are 1 kilogram, so it would be 2 kilogram. So that would be 3 Newton divided by 2 kilogram. Things are dropped, get attracted towards the earth, and that's called the force of gravity. Because that force is constantly applied to those objects, they're going to accelerate. And that acceleration is going to be on the surface of the earth is pretty much constant unless you go further up. But for all practical purposes, we have that acceleration due to the gravity, and that's about 9.8 meter per second squared. And we show that with the letter G, small g. Here I showed it with A, but we'll change that in a minute. And sometimes we use approximately 10 meter per second squared just to make things easier. So the force of gravity acting on a mass of this apple, for example, F, I show it with G, is equal to mass of the apple times G, because now G is the acceleration. This force is causing that apple to fall down. And that same force is acting on you and me sitting on our chair. Well, we have a mass, right? I want to find out what force of gravity is acting on me. I just have to find out what is my mass, okay, and multiply that by G. When I do that, what I have what we call the weight, my weight. So this is same as the weight of your body, weight of that apple. Now look, we're saying the weight is the same as force of gravity. So therefore, weight is equal to mass times G. So now look, weight and mass are two different things. You may have thought that they're both the same. No, weight is a force. Mass is the mass. Mass is what constitutes that object. All the cells and atoms that make your body or mine or this pen is the mass of this. But the weight is how much Earth is pulling me down. Because if I go to the moon, Moon is not going to pull me as much down. So my weight is going to be different. But my mass is going to be the same because I've never lost my, any part of my body. When I go to the moon, I'm still, intact. Please distinguish between weight and mass. So mass and weight are two different things. Another common misconception. So as you can see, on the Earth, you have certain amount of weight. Here, if you can see here, your mass is say 120 kilogram. Your weight is 120 times 9.8 or 10. So your weight is 1200 Newton. On the moon, your mass is the same, but your weight is 1/6 less. So if you go to near a black hole, which has a huge amount of gravity, you're going to weigh a lot. So here's an example. On the Earth, we just showed you that, 120 kilogram, your mass, your weight is 1200 Newton. On the moon, 120 gram mass times the acceleration divided by 6, because now acceleration due to gravity in moon is 1/6 of the Earth, so that's 200 Newton. Question for you. Consider a car pushed along a track with a certain force. If the force remains the same while the mass of the car decreases to half, the acceleration of the car, what happens? So the force is the same. Here's the one case, here's this other case. So you apply the same force, acceleration actually proportional to 1 over mass. This is 1, so it's going to go faster here. Acceleration is going to be that much here, whereas here it's going to be half of that. Then we reach to Newton's third law. Newton's third law deals with interaction between objects. What does that mean? That means whenever you touch something, it's going to touch back at you. So let's say you're sitting on your chair. You're pushing chair down by your weight. The chair is pushing back at you at the same force. That's why you're not moving, because the net force is 0. Look at all these examples here. Here you push against the pool wall. When you push against the wall is pushing back at you. That's the force that is causing you to move. You have to look at it from that perspective. You hit the wall with the car with a huge force, and the wall is hitting back at you at the same force. Or even if you push at the wall is pushing back at you. The forces are equal. At any instant when you touch anything, that's going to touch back at you with the same force in opposite direction. The billiard ball, the rocket, and the running, you're pushing against the floor. And the friction force of the floor is pushing back at you, so that allows you to move. All of these are part of the Newton's third law. Interaction between objects in action and reaction. The force of action is equal to the force of reaction in the opposite direction. And that's how we show it. Now, question for you. You have an accident here. Huge truck hits a small truck. Look at this. Question is, which vehicle would experience the greater impact force? Notice, greater impact force. Contrary to some common misconception, they both feel the same impact force. Whatever force that big truck is applying to the small one, there's at that instant and that time, at that bumper to bumper, the small car is pushing back at the same force. So these two forces are equal. This is action-reaction force. Even though if the big truck causes the small truck to move at any instant while it's moving, both forces are the same. This is counterintuitive, I know. Please, try to look at it from this perspective. At the microscopic point of view, when the bumpers are touching each other and the accident happens, these molecules are pushing those molecules, and the same molecules are going to push back. So all those forces add up to give you a total force on one direction to be equal to the total force on the other direction. As a result of this, we have a force, we call it a normal force or support force. Suppose your book is sitting on the table or you're sitting on your chair. Your weight, your force of gravity is pushing down on that surface. That surface is pushing back at you. So the net force is zero, so nobody moves, okay? Same thing here. Look at this one too. I mean, the net force is zero. Now, when you're looking at the situation like this, okay, and say you have an object here, let me try to analyze this for you. The force of gravity is always downward towards the center of Earth. So that's called Fg. And that is actually same as weight of that object. However, if you choose a coordinate system that is convenient, what you can do is you can decompose the vector, the Fg or W, which is the force of gravity. One component of this would be along the y-axis, and one component would be along the x-axis. So you can always decompose, you have a, let's say, coordinate system, and you have a, let's say, a vector, okay, A. You can decompose that. So you have AX and AY, okay? So in this case, I'm decomposing this to the x direction, FGX, let's call it FGX, and let's call this FGY. Now we said there's always a normal force, support force, that acts on an object perpendicular to the surface. There is a force here, I'm going to use a different color here, and that force is normal force. So look what happens here. You have a force, normal force, which cancels out with the y component of the Fg. So that object is not going to go fly off or is not going to go inside the inclined plane. However, there's a little force here, Fgx, that is causing it to slide down. And that's what this Fgx does. Now, if there's no friction, that thing is going to accelerate down and go faster and faster. If there's a friction, I'm going to use a different color for friction. Let's say the friction is going to be going opposite, and I'm sure that with a small f. Now, if the friction is same as that force of Fgx, then that block is not going to go anywhere, just going to sit there because all the forces are balanced. So that's how we incorporate the normal force or support force, we call it, balance it with the other forces that are involved in interaction for a body. So the question now is, a soccer player kicks the ball 1,500 Newton force. What happened? The ball exerts a force back at the foot, according to the Newton's third law, the same in opposite direction. When a cannon is fired, the acceleration of cannon and the cannonball are different because their masses are different. Cannon is huge. Cannonball is small compared to the cannon. As you can see, the cannon is a lot massive than the cannonball. But the force that is acting on these two are the same because the powder inside the cannon explodes and pushes both objects, one to the right, one to the left. So the cannon recoils a little bit, but the cannonball moves a lot faster because it has smaller mass. So I can show you that with this equation. So these forces on both the same. Because the mass of the ball is small, it's going to have a huge acceleration flying off. Because the mass of the cannon is big, it's not going to have that much. It's going to recoil a little bit to the opposite direction. So you see how that works? Okay, this is a good time to take a break, and let me pause